Hey guys, my name is Will Buchanan, and this is my Lab 5 involving magnetic braking with Faraday's law. So for the introduction, the lab involves the concepts of flux, EMF, and Faraday's law, and a couple other things, and uses the example of a magnet falling through a metal tube to display these concepts. The purpose of this lab is to gain a better understanding of what's going on when the magnet takes a long time to fall through the tube, and we use computational and experimental models to understand this interaction. So some key concepts include Faraday's law, which is found down here, Lenz's law, which just elaborates on Faraday's law, Ohm's law, the magnetic force, and Newton's second law. So for the experiment setup, the experiment involves dropping a magnet through a tube of aluminum and recording the time it takes for the magnet to fall through. So the system will be the falling magnet, and the surroundings are the aluminum tube and everything else. So for the procedure, you mark the north side of the magnet and record the magnet's mass, and then you record the dimensions of the tube, and then you drop the magnet through 5 times and take the average time. So here are the measurements of my setup, and on average, the magnet took 0.81 seconds to fall through the tube. And moving into the computational model, here are the same conditions, but just in the code. And here's the conditions of the magnet. And then here we're just setting up the magnetic field. And down here you can see the gravitational force. And then in this batch of code, you're dealing with the magnetic field of each ring, and then you're applying that to the tube. And then here you take the magnetic force and apply it to the magnet. And right here, you're getting the net force by including both the gravitational force and the magnetic force. And down here, we're using Newton's second law to determine the magnet's velocity and position over time. And in the computational model, here's the graph of the magnet, and it took 1.198 seconds in the computational model, so a little bit longer than the experimental model. So here we see experimental versus computational. It took 0.81 seconds in the experimental and 1.12 seconds in the computational model. So some possible errors of the experimental model include hand timing that could have been improved using a sensor or slow-mo video with a timer in frame to get more accurate times. And it's possible the magnet contacted the tube while falling. It was tough to prevent that. And it was just tough to record the time and drop the magnet and do everything else just with 2 hands. So maybe getting another person to help could have improved the experiment. And I thought it was interesting that the lab time was longer than that the experimental time was longer, because I would have guessed that things like air resistance and other factors would have caused the experimental time to be longer, not the computational. And then for the discussion, if the resistivity of the conductor was reduced as close as possible to 0, how would the magnet be affected? So if the resistivity was reduced to 0, the current would increase because those two things are inversely proportional. So then the increased current would cause the magnetic field to increase, and an increased strength in the magnetic field would cause the magnet to fall more slowly because it's the magnetic field that keeps the magnet from falling like normal. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So the holes or slots in the tube would cause the magnet to fall more quickly. And this is because taking away aluminum from the tube means the total induced current will be smaller, just because you're losing material and you're disrupting the induced current by putting little gaps in the tube rather than it being just one continuous tube. So the induced current would decrease and the magnetic field would get smaller, which would allow the magnet to fall quicker because there's less force against it or resistance against it as it falls through the tube. And that's all I have. Thank you for watching.